Hello everyone, welcome to lecture 9 of the online course on modern display technologies, flat panel displays. Today's lecture will be covering the remaining fundamentals of colorimetry. So here is the lecture outline. So we have discussed the first two topics, trichromatic space and CIE 1931 colorimetric observer in the previous lecture. Today we will go into details of CIE 1976 uniform color system, and then we will look into CIE CAM02, that is color appearance model, and then we will be trying to covering this color gamut in the next lecture. So these two highlighted ones, the black ones, will be covered in this particular lecture. So let us go back to CIE 1976 uniform color system. So if you remember, this is how the horseshoe kind of shape of the color system or the colorimetric space looks like, right. So we have seen this kind of map in 1931 color system as well, right. So what is the problem with 1931, sorry, not 61. So what was the problem with that CIE 1931 XYZ color system? Though they were able to describe the colors exactly, but there was a problem when you were dealing with color difference and tolerance. So a perceptually uniform color space is basically required for better color comparison, and this is where this uniform color system that was proposed in 1976 came into picture. So what is the problem that can be highlighted here? You can see this particular figure shows the McAdam ellipses. These ellipses are called McAdam ellipses. This basically defines a region where color difference are not perceptible to human eye with a normal color vision. That means any normal human will not be able to differentiate the colors which lie within this particular ellipses. Okay. So this is the 1931 XYZ or XYZ chromaticity diagram with this McAdam ellipses shown. Now if you observe this carefully, you will see that the blue region show smaller ellipses, means here the range of color where you cannot differentiate is smaller. That means you have basically got higher sensitivity here. But when you move to the red or the green zone, you can see that the ellipses are much larger. That means there are a lot of different colors which you can't basically differentiate. And note that these ellipses are basically 10 times magnified for clarity to show you properly. So in fact, in reality these ellipses are not that large, they are basically really small. So to better quantify the color difference between two stimuli, for example a real object that you can see and the image of that particular object, the same object that is displayed on a electronic display, you need to have a uniform color system. That means you require a transformation that can redistribute the color space more evenly according to human perception. So display is more about perception, right? Whatever is the real color that you are able to see and the color that your display is producing, there should not be any identifiable difference between those two colors, and that is why people have basically moved to this uniform color system in 1976. So this is a common uniform color system. It is also called CIE 1976 L star, U star, V star, okay, color system. So that is basically coming as a nonlinear transformation from the CIE 1931 capital X, Y and Z color system. So how this transformation looks like, we will show it here. So we are basically doing some sort of coordinate transformation from this CIE 1931 XYZ system to 1976 L star, U star, V star color system. So that is described like this. So L is basically defined as 116 y over yn to the power 1/3, okay, minus 16. So here this ratio, this is applicable for ratio which is greater than 0.008856, okay, and in this case your u and v will be basically 13 L u prime minus u n prime, and v will be 13 L times v prime minus v n prime. Now if this ratio y by yn is less than equal to 0.008856, then this particular equation can be used. Now what are these u prime v prime and u n prime v n prime? They are basically obtained from your capital X, Y, Z that you actually have from 1931 color system. So these are the equations that basically define those. Now you can see here u prime and v prime, they are basically dependent on X, Y, Z, and v prime also dependent on X, Y, Z. However, u n prime and v n prime, they are basically dependent on x n, y n, z n. Now what are these? These are basically the stimulus values of the reference light source, okay. Now since the transformation that you have done, so trichromatic space, if you see in 1931 system, this is x, small x and small y. So basically you are moving from small x and small y to u and v, or u prime and v prime. So this is how the CIE 1976 u prime v prime chromaticity diagram looks like, and here also you are having McAdam ellipses. So you can understand the transformation that you have done from small x to small y, okay, to u prime, or you can say u star and v star. They are basically linear, okay. The capital X is nonlinear, but this is linear, and the equations for the color mixing are still valid in this particular color space with some modifications. So as a result, what you have obtained, you have got this CIE 1976 L star, U star, V star uniform color system that is typically used in display application. So the reference light is typically a white point, such as daylight or black body radiation, which is used for describing the color performance of an object under light source illumination. Now when considering an emissive or transmissive display, your xn, yn and zn values will be set to 0, because you do not have a reference light source, because the light is basically inside and it is a transmissive display. So in that case, your u star and v star basically converges to this u prime and v prime that is shown in this figure. And here you can see that the ellipses, the McAdam ellipses towards the monochromatic wavelengths, they are almost identical in size. So it is not that you are more sensitive to one color and less sensitive to other. So this trichromatic space looks like uniformly distributed. So if you compare this with 1931 CIE XYZ system, you can say that this 1976 system, the color space not only improves the uniformity of color difference, but also the brightness difference is more uniform, because the Y and the L values, okay, that is where the game is, right, because Y is the brightness value in case of 1931, and here L is the value that is used for this 1976 color system, right. So the brightness difference is also made uniform. The Y value was the luminance that you have seen in 1931 system, that is basically proportional to the physical optical quantity. So which is this physical optical quantity means in watts, okay. Now your human eyes have nonlinear response, okay. So because of that, it is not appropriate that the intensity difference between two stimuli with the same color but different brightness should also be described using the Y value. So, in that case you will see that the L value that is used in 1976 color system is found to be more visually uniform in the intensity axis as compared to the Y values. Okay. So, what we understood, that L is proportional to Y to the power of 1 by 3 that you have seen here in the transformation, right. So, what happens, because it is to the power of 1 by 3, that means now the human eyes can distinguish a smaller change in luminance when the luminance value is low. This also tells you the fact that when the stimulus is dim, only a small difference and in luminance can basically result into a large change in the visual perception. When the stimulus is bright, it basically requires a large difference in the luminance to obtain the same change in the apparent brightness. So, in a display we basically use the term grayscale to determine the difference between the brightness level. For example, the darkest and the brightest grayscale of one primary color is basically 0 and 255 respectively. So, when you say 0 in the dark grayscale, that means that color is absent, and when you have 255 on the grayscale, that means it is the brightest of the particular color which is in the purest form. Okay. So, that way it is basically you can represent by 8 bits. So, if you look into the 3 different colors, it can be 2 to the power 8 into 2 to the power 8 into 2 to the power 8, that is like 16 million colors can be shown in this particular display. Now, the apparent differences in brightness, because any two adjacent between any two adjacent gray levels should be the same. So, here this figures basically plot the luminance, which is having a unit of candela per meter square, versus the gray scale. Okay. So, this is in a linear scale, this is in a logarithmic scale. So, what you see here, that the gray scale, the gray levels versus the luminance with linear and log scale, these are basically measured from a LCD monitor. Okay. So, they lit at the white points set at different gray levels. So, the monitor is basically turned on at different white point only you are seeing, but at different gray scale. So, the intensity is going to be different, that means the luminance that will be recorded will be different. So, here the gray level is 0, then 50, 100, 150, 200 and 255, that is the highest one, this is the lowest one, right. So, this is in linear scale, this is how you see it in log scale. Now, if you see the slope of this particular line in log scale, this slope basically gives you the gamma value, and this is typically 2.157 in this case, which is obviously larger than 1, but smaller than 3, right. Now, in this particular example, we consider the display to have gray scales starting from 0, 0 stands for black and 255 stands for white. That means anything in between 1 and 254 basically represent different gray levels from dark to light. Then the luminance difference between the grayscale 0 and 1 is smaller than that between 255 and 254 and 255, since the gamma value is not set to 1, because you have the slope is around 2.157. So, what is the real world luminance range? So, the natural light typically varies drastically from 10 to the minus 3, that is very low luminance. So, that is in candela per meter square. This is typically for the light that comes from stars. Okay. To 10 to the power 5 candela per meter square, that is in the broad daylight. So, you can see the range of variation, that is really big. So, more practically, these are like very extremes. So for an observer in a room during daytime without indoor lighting, the sunlight from the window may be as high as 10 to the power 4 candela per meter square. So that is typically the luminance that is there during a daytime inside a room when there is sunlight outside. So if you consider other objects in the room, they may be typically like 100 candela per meter square, and the dark region in the room could be 1 candela per meter square. So if you want to describe such a scene on a display, so what you require, you basically require a contrast ratio or dynamic range that should be higher than 10,000 typically, right. So consider the display that is basically shown in the figure. So this is the one we considered, the luminance versus the grayscale in a linear scale. Okay. So here the maximum and the minimum luminance value, as you can see, the minimum one is around 1.72 candela per meter square, that is for 0 grayscale level, and this is typically 87.6 candela per meter square for 255 grayscale level, right. So obviously this display cannot produce the luminance range in the real world, because here the contrast ratio is only 50.9, which is far below the one that we are looking for. We want to go somewhere close to 10,000. So the contrast ratio is very bad. That means here you can say that this 8-bit grayscale is not enough to describe the luminance detail for the real world, because you do not get enough contrast level. Hence the ITUR, that is basically the International Telecommunication Union, mainly in the radio communication sector, they basically, because they are the one that they broadcast the television signals and all. So they basically recommended a standard called BT 2020. So BT stands for Broadcasting Services, that is for the high dynamic range HDR. Okay, so that uses 10-bit or 12-bit. Okay, so you basically have more number of luminance steps now. So you have, with 10-bit you can have 1024, and 12-bit you can have 4096 luminance steps. So if you want to display HDR content, okay, that is basically the high dynamic range content, typically your display should exhibit the maximum and the minimum luminance at say 1000 and 1000 candela per meter square, and the lower one, the minimum one, should be around 0.01, so that you can hit that contrast ratio of around 1 lakh, right. So we only consider the contrast ratio of the display in this particular stage when considering the ambient effect, means what is the ambient lighting condition and all those things, the situation will become much more complex. So only with this kind of thing we are trying to tell you that how you can differentiate between the bright and the dark in different cases. So for high dynamic range, you should go for this kind of luminance values, the maximum and the minimum limit, to get a good contrast ratio. Now let us move on to the color appearance model, that is called CIE CAM 02 color appearance model. So the CIE 1931 XYZ and CIE 1976 Uniform Color Code System, that is UCS system, these are like successfully used to describe a single color batch and also the difference between the two colors, right. However, when you are viewing an image from a display, there are many colors and brightness levels on the screen. In addition, the color appearance is basically getting affected by the background and also the surrounding of the object that is in question. So here is an example of a round cylinder being placed on a checkerboard. So this is an illusion of checkerboard with shadow. Okay. So the light source obviously is behind this cylinder, so that it can cast a shadow on the checkerboard. Now what is happening, you are basically looking at this point A and B. So these two boxes, okay. So the visually you can see that the A region is basically a black square, okay, and B region is a bright square, okay, and this is like, you know, the appearance of A is significantly darker than the white square, right. So you can clearly say this is dark and this is bright square. Now as soon as you draw this straight gray color lines with uniform color and now try to look into these two squares, nothing else has changed, okay. So this straight gray line with uniform color that is basically intersecting the region A and B demonstrates that these two squares are basically, they have exactly same brightness and color, okay. So they are not different, they are basically same. So in other words, okay, this in figure A, the square A and B basically appear different only because of their surrounding, okay. So this shadow played an important role, okay. So such an effect cannot be accounted for by this kind of color systems, right, because this is something external factor that is basically making a difference in the opinion of the color of the two boxes, right. So because the existing systems cannot work here, a new model describing the color appearance, so how the color is appearing, that is required, and one of the most successful model is called CIE CAM02 model. So to construct the color appearance model, we must first define a few terms. The key concept in color appearance is the brightness, that means the absolute luminance value. So that is certified by capital Y in CIE 1931, that we already know. Next thing is lightness, that basically accounts for the relative brightness that is influenced by the surroundings. So take an example, when we read a book under dim and bright ambient light, the white region exhibits lower and higher brightness, right. So for dim light, the white background will also look lower bright, and when the bright ambient light is there, your white will look more brighter, right. So depending on the different illumination condition, the white region looks different. However, the lightness of the white region basically remains same, because the reflectivity of the white paper is same regardless of the luminance level. Next important concept is hue. Hue is basically the perceived color type, whether it is red, yellow, green, blue. What is that perceived color by human eye? Next important concept is colorfulness. So colors difference from an achromatic color. So that means achromatic colors are like where there is no color, like white, gray and black, okay. So if you take a color like deep red, that means the hue of this color is red, and it is deep red means the colorfulness is really high, okay. And when you talk about the achromatic colors like white, black or gray, they basically has no hue. The next important concept is chroma. So this is basically the relative colorfulness, which is analogous to how lightness is related to, or how lightness relates to the brightness. Then you have saturation, that tells you the degree of colorfulness relative to the chromaticity boundaries. So highest saturation can occur with monochromatic light, which are at the boundary of the chromaticity diagram, means that will tell you the purest color for that particular color type. So we can show this using this particular appearance model example. So here we will also take into consideration the effect from surrounding. Okay. So, that can be shown using this model that is given in the figure. So, here the color appearance of the central region, which is the stimulus, is basically affected by the background and then the surrounding field. Now, the stimulus is a small area and the background, okay. These two things basically show uniform color areas, right, with angular sizes of 2 degree and 10 degree to the eye. Now, the input parameters for the calculation that is considered inside the CIE 1931 XYZ color system, they are the values of the stimulus and the white reference that considered together with the luminance of the background and the surrounding field. Also, here the viewing conditions, like whether it is average, dim or dark surrounding, that should also be taken into account. So, with that, if you use a full description of the color appearance, that can be described by obtaining the values of all the parameters described above, something like brightness, lightness, hue, colorfulness, chroma and saturation. So, this basically tells you complete picture about the color appearance. Okay. Although there are still some constraints, such as treating only static images without considering the dynamic effects. Despite all these things, CIE CAM02 model is one of the most successful color appearance models describing the surrounding effect of the image. So, if you consider this particular image back that we considered earlier, here you can see that with this particular model you can qualitatively explain the illusion that is seen here. So, how to explain this? You can say, although the brightness of the shadow region is gradually reduced, this change is typically disregarded because human eyes tend to focus on the sharp edges, okay, such as those basically defining the checks. So, your focus will be main on the sharp edges, okay, not on this gradual decrease in the shadow darkness. So, that is how your region B is found to be brighter as compared to the surrounding checks, okay, which basically provides a higher lightness, and that is why it appears brighter than the region A, okay, although the absolute brightness of the two regions are basically exactly same. So, it is basically because of the shadow that is giving you that effect. So, although the brightness of these two regions are exactly same, because of this having higher lightness, this appears to be brighter than region A. So, this is how this particular CIE CAM02 model can basically explain qualitatively this optical illusion. So, with that we conclude this lecture. If you have got any query regarding this, you can drop an email to this email address mentioning the course title on the subject line. Thank you.